we are starting the fourth day of the FTAG 2016, FTAG-XI, and first talk is by Romesh Kaul for first and second order formulations of gravity equivalent. Yes. Yeah.
So let's start. That's the title of my talk, our first and second order formulations of gravity equivalent. This is work done with Sandeep and Sen Gupta, and there's a paper on archive recently, I don't know the number, but last week or a week before.
I can tell you.
So one way to describe the theory of gravity is through Einstein-Hilbert action functional. And we'll take the signature to be Euclidean so that we can have a carry to many minus signs here and there. So the action is root G, G mu alpha, and the Riemann curvature. Riemann curvature is defined in terms of Christoffels. And Christoffels are
Right side.
okay. We could add cosmological constant or matter or anything to this margin, but that's not going to change what we're going to say. So the functional integral, this action functional for pure gravity on its own is of significant interest. The point to note here is that the metric here, G mu nu, is the independent field action, whereas Christoffel symbol is not independent. It depends on the metric. So the variation of the action functional are done with the independent field, that's the metric. That gives, we have the Euler-Lagrangian equations of motion, which are the same as Einstein field equations. R mu nu minus half G mu nu R Z. So, and this is an interesting structure. These equations admit black hole solutions. But important point to register is that solutions of Einstein equation of, that is in absence of any matter like fermion, by constructions do not possess any torsion. And the important point, another important point to register is by construction, the metric here is non-degenerate, it has no zero eigenvalues, so that its inverse and determinant are defined. This formulation of gravity is also called second order formulation, in contrast to the formulation that I'll describe to you, which is called first order formulation. So an alternate formulation of theory of gravity is the first order formulation. Describe the Hilbert-Palladieri action function. In this action function, we have two independent fields, tetrads and the connection fields. Action is integral d mu alpha beta epsilon I j k, tetrad e mu I, e mu j, and r alpha beta k. R alpha beta kl is now, this curvature is now really the field strength, it's not Riemann curvature, it's the field strength of the gauge field or gauge connection omega ij of the local Lorentz group SO4 of Euclidean gravity. And it's defined in the standard way, antisymmetric derivative of the connection and product of two connection fields and in antisymmetric. Just for completeness, the completely antisymmetric epsilon symbols here, epsilon mu nu alpha beta and ijk are having values 0 or plus minus 1, where we have normalized epsilon x y z tau, I just put deliberately topic to remind us that we will Euclidean gravity, plus 1, and epsilon 1 down 1, 2, 3, 4 is 1. Tetrad is to be thought of as usual way the square root of the metric. So product of two tetrads is the metric, but product is run through the flat metric delta Ig. So like I said, both tetrad field E mu I and connection field omega mu Ij in the action field are to be taken independently. So to study equations of motion, we must vary with respect to these fields independently. So the equation of motion, when you vary with respect to tetrad, is epsilon mu nu alpha, epsilon ij kl, tetrad e nu j, r alpha beta kl. And these are 16 equations. And then when you vary with respect to connection, you have the equations of motion, epsilon mu nu alpha beta, epsilon ij kl, tetrad e mu k, covariant derivative is the nu of tetrad e alpha l. And these are 24 equations. Covariant derivative here is covariant with respect to the local SO4 transformation. There is no gamma here. So what we have to do is we need to solve these equations. So consider the first set of equations. The second set of equations here. There's an alternate way of writing them. These set of equations, I'll write them in an alternate way. There's an alternate way of writing that. E mu L, covariant derivative nu of E alpha, mu nu alpha all antisymmetrized, Ij antisymmetrized. These are the same 24 equations that we wrote earlier in a slightly different way. Now, if I assume that tetrads are invertible, that is, determinant of tetrad is non-zero, so then I could define an inverse, E mu up, I down, in the standard way. Then elementary exercise tells me that if I multiply this set of 24 equations by inverse tetrads a few times, these 24 equations can be easily solved to yield another equivalent 24 equations, and those are these. Covariant derivative mu of tetrad mu nu, antisymmetrized mu nu is 0. This is exactly the torsion. So what this tells us that for invertible tetrads, the set of equations of motion imply that the torsion is 0. Now these 24 equations can be further solved for 24 connection fields, and that is the standard Levi-Civita connection fields. Omega mu ij is half E nu I, covariant derivative, ordinary derivative, antisymmetrized, and so on and so on. So to repeat, thus we find that through this set of equations of motion, the connection fields are not independent but are given in terms of the tetrads and the derivatives.
Only in the absence of fermion.
Epsilon matter. Now let's look at other set of Euler-Lagrangian equations that we had, and they can be rewritten in this way: E mu I, R mu alpha, Jk, antisymmetrize these three set of indices. These are the same 16 equations, and multiplied by inverse tetrads, this 16 set of equations can be reduced to equivalent 16 set of equations: R alpha k minus half E alpha k, R equal to 0, where R is constructed from the field strength by contracting a pair of indices to a tetrad, inverse tetrad, and R is the scalar construction of that. So important point to instead here is that for invertible tetrads, the solution of equation of motion will be all torsion free. And also further, above equations are really Einstein equations, which becomes transparent by realizing that for invertible tetrads, the local Lorentz field and the Riemann curvature are related. So the local SO4 Lorentz field can be converted through an inverse tetrad and a tetrad multiplication into Riemann. Thus for invertible tetrads, the first order and second order formulas are exact.
So you are saying that this relation is only true for invertible?
That's what we're repeating again and again to emphasize that.
Right.
In both these formulations, the configurations that satisfy vacuum equations of motion, to remind us, for the first order formulation with invertible tetrads, do not possess any torsion. And this is both necessary and sufficient. Torsion is introduced in both these frameworks through matter couplings, say through coupling of fermions. But before we attempt to exert equivalence of two frames, let's examine the action function of a first order formulation a bit more closely. So recall the action functional. Excellent functional was integral d4x, epsilon mu nu alpha beta, epsilon ij kl, tetrad e mu I, e nu j, r a alpha beta kl. But this is the SO4 field strength. Notice this action is defined both for invertible as well as non-invertible tetrads. There are no determinants of tetrad in this section, there are no inverses of tetrads in this section. So, it's reasonable to expect that it would admit configurations which involve degenerate non-invertible tetrads. Such configurations would be particularly important in quantum theory, where we will need to integrate.
In the earlier picture, when you work out from the action to the equations of motion, do you use explicitly the invertibility of the tetrads?
Nowhere, because inverses are not there in the action, so we don't use an invert.
Because
In the first set of equations. But when I make a connection with the Einstein field equations, there I use the inverses. So those steps are valid only for invertible tetrads.
in principle variational, when you do variations, we have the space of configurations of all tetrads where some of them can be even non-invertible.
That's the point here, because this action principle that I have does admit that.
Do you use somewhere the Kata's equation? There is one Kata equation which relates torsion to the curvature, which is a kinematic equation.
I don't use that. I don't use any of this. I just follow this as a simple field theory, go step by step, use no input from anywhere else except the action. There's no input from any other thing. Just write down the action, follow the standard variation principle, work out what you get. No external input beyond the action. And maybe when I wrote down, maybe I should. When I call this object torsion, somewhere I wrote it, right? Maybe let me go back. When I call this object torsion, that has implicit definition of what torsion. So for me, torsion is only this object. How do I relate it to gammas? Is not my definition. My definition is that this being zero or non-zero is torsion. And when it is zero, it also reflects, if for invertible tetrads, if this is zero, that also is equal to saying that gammas are symmetric.
But I can have this zero for the non-invertible as well.
Not the full four, it is a full equation, some part of it, some part. Not all components. So we were here, we are already gone ahead.
Go back.
So we were here. So if we find, let me go back and where I was making a point that in quantum theory such configuration would be important. So such configurations would be particularly important in quantum theory, where we would need to integrate over all possible configurations, including those with degenerate tetrads in the functional integral, each with a weight exponential s for the action of that particular configuration, as dictated by Feynman half integral quantum theory. Now these configurations, unlike the one for invertible tetrads, could as well possess torsion even without presence of any torsion-inducing matter. So thus we ask even at the classical level, we ask the following questions. Are there any degenerate tetrad solutions of Euler-Lagrangian equations of the first order formulation? Do such solutions possess torsion even without any matter? Do these configurations have finite action? If we find such solutions of the equations of motion, then the two formulations from gravity theory based on the Hilbert, Einstein-Hilbert and Hilbert-Palatini action functions would not be equivalent even classically. So let's start with it. Let's think of the simplest case that we have one zero eigenvalue in the tetrad. So let's start with degenerate tetrads with the 1 0 eigenvalue. So you can write a tetrad as a 3 × 3 block with all the zeros here, and I take this to be the tau direction, time direction. The Euclidean doesn't make much sense, but just for names. So this block, 3 × 3 block, has no zero eigenvalue. It's invertible. So now metric becomes again a degenerate. It's a 3 × 3 block GAB here, which is the product of two triads. And this triad, determinant of these triads, I'll call E, is non-zero. Because by assumption, there's only one zero eigenvalue.
Can I ask an answer? Now that we are starting with this, first thing is that G mu equivalent to E mu I, then does not that automatically says that since the metric has to be invertible, that definition is true only when E mu paradigm is invertible.
No, metric is not invertible here. 4 metric is not invertible here.
So 4 metric is also
It's degenerate. That's it. In fact, title of the paper was Degenerate in Space-Times.
Yes.
Romesh, I just wanted to ask you one question. If the metric is not invertible, then how do you construct this epsilon mu rho under the 4 index antisymmetry Kaul? Because that requires root G.
No, that doesn't require root G in my definition. That's the reason why I emphasize what it is. I would say sometimes people do put root G. I don't put root G. It's simply number 0 plus or 1, plus 1 or minus 1.
There's already a tensor density.
Yes. I don't need that.
This quantity by square root of it. So it is epsilon and u epsilon before by square root of it.
Yeah.
That was the reason I made the trivial statement that to make this get clarity that my epsilons are constants.
That's why the determinant of epsilon is not there in the action.
That's why I also did that. So we denote the inverse of the triad by E hat, so that we don't confuse it with the E upper index objects that we had induced for invertible tetrads. So we define them through the usual way. We remind ourselves that all the these tetrad fields, non-zero tetrad fields, or these triad fields, in general depend on all the 4 coordinates x, y, z, and tau. And what we said earlier also, 4-dimensional length element is 1 0 eigenvalue, so nothing from here, GAB, dx, dx. Using this tetrad, we need to solve the equations of motion. So let's do that. Let's go back to recall the 24 connection equations of motion. These were what it is: E mu I, covariant derivative d nu, E alpha j, mu nu alpha intersymmetrized, E I j intersymmetrized. Now, unlike the case of invertible tetrads, these 24 equations could be solved completely for 24 connections for invertible tetrads. But here, these cannot be solved for all the 24 connection components. Some of them will stay undetermined because there are 2 less equations in fact, because of the fact that E is degenerate. It turns out that 12 of the connection fields are fixed through these set of equations, and 12 connection fields stay undetermined. Now, after a bit of algebra, it can be shown that the most general solutions of this set of equations are provided by configurations which satisfy the following constraints. First is that tetrad should be covariantly constant with respect to tau. Tau is the time direction, in the direction in which the zero eigenvalue lies on the tetrad. And this fixes what the connection omega tau ij components have to be in tetrad. This can be solved. So 3 connection components are fixed. Next, these equations of motion imply that the connection component omega tau 4k should be 0. So that fixes 3 volt. Then omega A 4k, these are 9 fields here. I could rewrite them, I will introduce a symbol for it, which is MAK, and also that these 9 fields equivalently can be written in terms of as matrix MKL and resolved in the base of tetrads, in triads, non-zero, invertible triads. So in general, these are 9 fields, or these are 9 fields, these are 9 fields. But what these equations of motion tell you, that the antisymmetric part of the matrix MKL is 0. So that leaves that MKL is only symmetric. So 3 more components have been fixed, 6 have been left unfixed. These are symmetric components which leave it MKL, symmetric MKL. Next we write omega ij as omega bar ij E plus kappa ij E, where omega bar we construct in terms of the triads. So it's a Levi-Smith connection in terms of the triads. So this is the connection which is torsion, this is the torsion-free connection. So we separate a torsion-free connection component of this, and the rest of it, kappa alpha ij, is the contortion piece. And kappa ij are again 9 fields. We reparameterize them as epsilon ijk, nak, introduce a new set of 9 fields, nak, and that can also be equivalently written in terms of a nkl, a 3 cross 3 matrix. nkl, the 9 fields would be here. But again, when you put this back in the equation of motion tells you is that nkl cannot have an antisymmetric part. So nkls are symmetric. So what has happened is that this set of equations of motion has fixed all the connection component except the 6 in the symmetric nkl and 6 in the symmetric nkl. So 12 are not fixed, everybody else is fixed. We notice here that 24 connection fields, only 12 get fixed. The rest of the 12 components are represented by the symmetric matrix M, Ij and Nij are not fixed. Just to reassert that these set of constraint or equations of motion are exactly equal to original 24 equations of motion for invertible, for one zero eigenvalue tetrads. An important property note here is that these equations imply that such configurations would generically have non-zero contortion even when the even in the case of pure gravity without any matter fields, such as photons. Now let's look at the other set of 16 equations. The other set of field equations that we have here. Just to remind you, go back to a question earlier, did we ever use inverse tetrad in getting these equations? There is no way. See, these equations also motion also don't see any inverses. So we have 16 equations. Now a little bit of analysis, it can be shown that the most general solution of these equations can be provided by configurations which satisfy 16 constraints. First one is that inverse triad E hat Ij contracted with R tau R A Ij component is 0. Second set of equations is that Ra tau 4k is a covariant time derivative of the MAK. This is the MAK was a renaming of the connection component omega A 4k. So that is 0. So this object is covariantly conserved with respect to tau. Then we have another set of equation is that inverse tetrad EAK contracted with RAB4K is this combination and a covariant derivative of A with respect to the torsion-free connection omega bar of MIL, and MIL is a renaming of the 6 fields in this particular way in this connection field.
So roughly trying to see a correspondence between the usual Einstein equation and these. The first equation is something like the R naught naught.
R not I
R naught I.
or R not J.
R naught K also. That's your
Yes.
First equation. And then last equation, this should be exactly like the Einstein equation with the 3 metric in multiple.
This one.
Ah.
Well, this is not, but I will make it. Just give me a few moments and I'll solve these equations and get you an explicit answers.
No, more than the solution, I'm interested in how do they formally look like the Einstein?
No, they don't. They don't.
There's no way I can get to.
They don't.
But you have used Euclidean metric.
That is not essential for
That's
us.
not,
That's
even
not
in the
essential.
Lorentzian,
Yes.
the whole
Yes,
thing will go
yes.
through.
Go through. But I want to, you say, I probably won't expect that at least your 3 by 3 matrix, which is invertible.
It's not the same set of equations that be the 3 by 3 of Einstein's set.
Einstein.
It's
That-
not the same
yes,
set of
it's not the
equations.
same.
Otherwise, you would not have torsion come in game.
Yeah.
So, and the last one is a single equation that is inverse inverse triad AI, EBJ, contract with RABJ, omega, make a scalar out of it. Expand RABJ omega in terms of the connection, torsion-free connection omega bar that we defined, and then it has additional pieces Mij, Mji minus Mi square and Mj square, and Nij, Nji minus Ni, and that is equal to 0. Recall, we had broken omega Aij into the torsion-free part and the contortion piece. And contortion piece we had parameterized in terms of these NKL matrices and symmetrical matrices, and that's what these NKLs are. And M's are, just to remind you, components of this connection being written in a different way. Now, if you look at this first equation, it's easy to demonstrate that this is identically satisfied by all configurations that satisfy the earlier set of conditions we had on tetrad connections. So this gives us no new information. And this set of equations, the next two sets of equations, they can be solved right away by taking AMI to be lambda as space-time constant times the triad field. These two equations are satisfied completely by this set of solutions. Then for this solution, Mij, which was here, is simply lambda times delta Ij, so Mij Mji minus Mij is minus 6 lambda square. So I can put this minus 6 lambda square and rewrite this last equation. This is the only one that is not solved, everything else has been solved. Rewrite it in the following way. This allows to rewrite as the last condition as on the curvatures as the combination zeta, which is Nij and Ji, trace of the squares of n's minus square of the traces, is 6 lambda square minus c minus this scalar, 3 scalar kind curvature. So all we need to now find a set of new solutions is to find a set of triads which will solve the earlier set of equations and then evaluate the corresponding spatial 3 curvature, this object, to fix about the combination zeta. And that would be that will complete this the sequence of finding a solution. Let's do that now. We shall do that now, and we'll immediately realize there are many possible solutions. There are a particular set of solutions for homogeneous 3 geometries described by triads ER. As you may know or may not know, that homogeneous geometries, 3 geometries are completely classified and they fall in 8 classes. Which are the 8 classes given by Thorson's model 3 geometries. So the names for these geometries are the simplest one is just 3 Euclidean space, 3 sphere, 3 hyperbolic space, S2, 2 sphere cross an R1, 2 hyperbolic 2 space cross an R1, and then there are special names given to other 3 for certain reasons, certain properties they have, mathematical properties they have. The names given to them are Sol, Nil, SL, 2R, delta. So these all 8 D geometries provide solutions to this set of equations.
What is S bar?
S bar.
SL2R. You have written SL2R.
This is a bar as a symbol on it to indicate something of SL2R.
Must be the
Not all of
universal
SL2R.
cover.
Covering,
No,
I think.
no, it's not that. It's something
Ah.
else in this context.
Mm.
So anyway, so that's a symbol for us. Let's now present a few examples. In the paper I mentioned, we have listed all the 3 matrix, all the 8 matrix there, and they analyze their properties. But here I'll present you only 3 examples. Simple is the hyperbolic 3 geometry. Metric is given by, this is a 4 metric with one eigenvalue degenerate, L square by Z square dx square plus dy square plus dz square, z greater than 0. Now it's straightforward to read off what are the corresponding triads associated with this metric. There are 3 non-zero triads, diagonal ones, each one held by Z. And construct the torsion-free connections for them. There are only 2 non-zero components here, and corresponding field strength for the torsion-free omega. So there are these. Now this scalar spatial 3 curvatures, this can be constructed from here, and this is minus 6 by L square. That gives us final extent. That the zeta, which is the special combination of the contortion matrices, has to be 6 lambda square space-time constant plus 6 by L square space-time constant. So this has to be constant, parameterized by 2 constants. So that gives us the first solution. Second solution is sole geometry. Degenerate 4 metric is exponential 2z by L dx2 exponential minus 2z by L dy y square and dz square. The triads and restrained Levi-Smith connections and curvature components can be constructed, and they are these. Ex1 is E. This E is triad and this E is exponential. Ez by L, Ey2 is exponential minus z by L, and Ez3 is 1. And these are the Levi-Smith connections, torsion-free connections, and corresponding to the curvature components. And the scalar 3 curvature is minus 2 by L square. So final constraint now is, again, 6, zeta is 6 lambda square plus 2 square. Again, this combination has to be a space-time constant parameterized by 2 constants. So let me now go to the third example. The third example is given a name called nil geometry. The metric here is dx square plus dy square plus dz minus x by L. L is some constant, dy square. Again, you construct the non-zero components of triads and associated Levi-Smith connections and curvatures. So they work like this. The scalar 3 curvature turns out to be minus 1 by 2L square. So the final constraints we have from the curvature equation, the zeta is 6 lambda square plus 1 by 2L square.
So so zeta is always constant.
Zeta is also constant.
So in some sense it's well, analogy with the Einstein case will be like it's RAB equal to lambda GAB.
No, but constant which changes from geometry to geometry. Every geometry has its own constant. Every solution, every solution has its own constant.
So okay, so there are more than, so you have more than one such solution.
It's a parameter of the solution.
Solution.
Yes.
Can I ask,
It's parameter solution, you want that.
may I ask a question?
That's in the
Yes,
second
please.
aspect.
All these look like R3, topologically R3. All the matrices you have given. I am not talking about the vertical aspect. Topologically R3.
Not H3 is not that.
Yeah, of course it is. It's very
Boundary.
different.
There is a boundary.
You know, H3 is a hyperbolic space
Upper
on the
upper.
upper half plane. There is no boundary. There is no convective.
Right, okay, all right. Let's have.
Now, the question is, we are changing the metric and you are saying, there's, Torsion is saying it is homogeneous. I am familiar with the word for the compact Torsion geometry, not this one.
This is the same.
But these are not complex spaces.
It doesn't matter, those are also,
What is a group that is acting to say that it is homogeneous?
see, those are why these names, different names come in. There are different sets of groups that come from different geometries.
Not all this.
No, it's one. See, the claim is that there are only these 8 homogeneous geometries. So 3 of them are isotropic. The first one is E3, S3, and H3, and other are known as
H3 we know.
Yes.
It's SL2C.
Yes.
Or the Torsion group, but
Now, it doesn't give the topology classification because topology classification is not done. Each E cannot be done perhaps. Because so within each geometry, you would have all varieties of topologies. But I don't know, maybe we can talk about, discuss what you have in mind. So what we have constructed here is a variety of solutions of the classical equations of motion in the first order formulation with degenerate tetrads. And to repeat, these all generate contain torsion. The torsion was parameterized through the symmetric three-prosthetic matrix NKL, where contortion was defined as epsilon IJK NKL EA. Now components NKL depend on all the 4 coordinates x, y, z and tau. So the 6 components are all independent except for one constraint they have to obey, which is the zeta constraint. That this combination has fixed values as dictated by various solutions. Now, unlike the usual framework where torsion enters through matter coupling such as fermions, we have here solutions which exit torsion even in pure gravity without any matter fields. So clearly, first order and second order formulation of gravity are not equivalent even classical. Let's try to understand the nature of geometry that these solutions represent.
But by the way, this criticism also raised by Witten's formulation of 2% gravity, the Chern-Simons gravity.
What is the criticism?
Same thing. If you have to assume invertibility of metric to get standard gravity.
Yeah, but what is the criticism?
It's not gravity. It is
No, no,
something
one
else.
phase is gravity, there's in addition to another phase in this theory. What is that, think of it as that in this theory there are 2 phases. One is the standard conventional gravity, the other phase is not standard conventional Einstein geometry. Now, if it has any meaning in physics meaning, that is different thing. In Chern-Simons theory, the physics meaning, well, I don't know what Chern-Simons theory is. There's a physics meaning, three-dimensional gravity and the thing. So it's a mathematical theory, it can be solved exactly. That is what this is, their one is. So it's a mathematical model, there's no criticism. I don't know if it's called criticism.
Criticism means that it does not mean Einstein gravity.
It doesn't mean Einstein gravity, that's a statement, it's not a criticism.
It's not supposed to mean.
It's not supposed to.
And three-dimensional theory is not again Einstein gravity. So three-dimensional Einstein it doesn't look like a corresponding 4-dimensional Einstein gravity as it would have been in 3 dimensions.
Right.
The word criticism doesn't make sense in this context.
Yes.
Statements can be made.
Yes.
One. Second is that not only that, you would then have the same criticism for loop quantum gravity. Loop quantum gravity is based on Hilbert-Palatin action, which is possible as an invertible tetrads.
Govindraji would say, I have no problem with that.
No. So we will not call criticism. That's a description, the property of the theory.
Romesh, are you going to address the question of finiteness of the action for this solution?
Oh, maybe I didn't do that. Yes, for all these solutions, if you evaluate the action, it is 0.
0.
It is 0. Or for all these class of 8 solutions, not only R class, all solutions that satisfy the set of equations that we have written down. But the Euclidean action in the Euclidean theory is exactly 0.
I may not write that this because it is a wedge of 4, is a 4 form as written, and if two of the entries become, or there is some linear relation between the forms, it will become 0.
That makes some components to 0, but not all.
Any linear relationship.
Some component makes that you need equations of motion to fix some components to make it 0. It is not a property.
Not a priori. At the solutions, as you were asking.
Yes, at the solutions.
There is some kind of a linear relation between the, it's a 1 form cross 1 form cross a 2 form, right? There is some relationship between those
There's some,
Forms, yeah.
no, the one form, for the components where it is non-zero, R turns out to be 0 from equations of motion.
Okay.
And for other places where one forms are zero eigenvalue, R is irrelevant. So some components go from the fact that it's degenerate, something is left behind that is taken away from equations of motion.
But this is zero only for these solutions. There could exist solutions
But
for which that
with
is
one zero eigenvalue, it's always zero.
always zero.
Always zero.
Right.
In fact, even for 2 zero eigenvalues, it's always zero. For 3 zero eigenvalues, also it's trivial.
No,
So
no,
let's
one
not,
zero,
let me
one-
not go into that.
One is
Four
good
zero,
enough.
One is good enough.
Yes, so let's not, definitely not go into that.
Right.
So we are trying to now, let's understand the nature of geometry of these new solutions. Clearly, they don't represent the usual geometry as seen in Einstein gravity. To analyze this question, let's go to the flat space-time limit. So, to be more definitive now, I'll also use Lorentz signature. This whole discussion is valid irrespective of what signature you have. In the flat space-time, the square of the infinitesimal length element with Lorentz signature is dx square, dy square plus dz square minus c square t square. Now, degenerate tetrads would correspond to a limit where this GTT component, which is c square, goes to 0. So this constant that you have put in the length element, this may go to 0. That's the limit of degenerate tetrads. Now, the length element stays unaltered under the change of inertial frames. So dx square plus dy square plus dz square minus c square dt square is same as another frame, dx prime square, dy prime square plus dz prime square minus c square dt square prime square. Everybody knows the Lorentz transformation leave this length element in way. So let me remind ourselves what the Lorentz transformations are. Dx prime is dx minus vt divided by square root 1 minus v square by dc. Dx and dy is not changed, dz is not changed, dt prime is dt minus v square by c square dx divided by square root of 1 minus v square. And in this transformation, we have introduced a parameter v. This is a transformation in the 0, 1 plane. We have introduced a parameter v, and c is a constant. And this transformation tells us that v square is bounded from above by c square. And this v square is immediately given an interpretation as relative velocity. So v is d by dx for delta x prime being 0. So that's what it is. What does it tell us? It tells us it's the velocity of a fixed point in the dashed frame as measured in the space-time of the undashed system. Now there's something else. This is not the only transformation that leaves this matter in this length element invariant. There is another one which is not very well known. Not so well known, there is another way of writing transformation that leave the dx square unchanged. And this is N.D. Sen-Gupta, 1966.
Tachyon. Tachyon.
No, it's not a tachyon.
No, it's not taken.
Tachyon is within the same system, only velocity goes above c.
Yes, exactly.
So this dx prime is dx minus c square wt divided by 1 minus c square w. Notice c square w square here and v square c square here.
Which is like tachyon, but less in
And y's and z's don't change. dt prime is dt minus dx by w divided by square root 1 minus c square by w. Now these transformations are defined when the parameter w that has been introduced is bounded from below w square from below by c square, this parameter c, this constant parameter c. W, despite its dimensions of velocity, is not to be interpreted as a frame velocity. It rather represents now, if you look at, W is dx by dt, but dt prime 0, not dx prime 0. So it's not really a relative velocity. It's something new with the dimensions of velocity, but what it measures is the rate of change of an event which occurs at a fixed time in dashed system as measured in the undashed system. Clearly, these are dual to each other. Space and time, in some sense, are interchanged. Now, it's of interest to study these two types of transformations in the limit c going to infinity and c going to 0. Now, recall Lorentz transformation. They have c's can be taken to infinity here, and they reduce to standard Galilean transformation. dx prime is dx minus vt, dy prime is dy, dz prime is dz, dt prime is dt. Now, on the other hand, c going to 0, it is the second transformation which is appropriate. So you will get the second transformation again, where take the limit c going to 0 in this. That gives us dx prime is same as dx, dy prime is dy, dz prime is same as dz, dt prime is dt minus dx. Again compare. Here time is fixed, here space is fixed. There is an interchange of time and space that is happening. To give you the exact reference on this is that N.D. Sen-Gupta on an analog of Galilei group, Novo Cemento, 1966. So what do we see? Thus finally we conclude, whereas invertible tetrads correspond to the usual Einstein curved space-times, the degenerate tetrads in the first order formulation lead us to another phase described by the curved space-time generalization of Sen-Gupta space-times. Now, a specific class of degenerate tetrad solutions are associated with the Thurston's 8 model geometries. Gravity theory in the second order formulation based on Einstein-Hilbert action functional and the first order formulation based on Hilbert-Palatini action are not equal and even classical. The phase with degenerate tetrad leads to solutions of equations of motion which generically carry non-zero torsion even in absence of any torsion-inducing matter. In contrast, in the second order formulation, we need matter fields such as fermions to introduce torsion. Thank you.
Okay, first.
No, take that. No, you say
Yes. Okay, go ahead. What? You are asking question?
Yeah.
You are talking.
No. I just asked for who is in English and
No. Okay.
No.
Go ahead.
Romesh, you took the time like eigenvalue 0.
Yes, time direction again. Yes.
One time like that 0. And then you got a corresponding geometry, your Sen-Gupta geometry, where it corresponds to the c going to 0. Now suppose I have taken one space like direction 0.
Two other values.
No, only one space.
Only space like.
He's talking about this is a Euclidean geometry. I just take time to be any space direction. So what is how it happens? Deliberately I label it to tau.
One space like my question is, what will be the corresponding geometry?
I don't know. I
don't
don't know.
I just.
Because I could relate it to this kind. That's why I deliberately put it in tau direction and then the Lorentz time. That
I know that.
It's a deliberate choice precisely for this reason because I don't know where it is. I know what it is.
Just an inquiry. Do you anticipate any change in the calculations, particularly either in quantum cosmology or in some other fields? Because if you introduce the contributions coming from these extra terms,
I have no idea. I am not a gravitational physicist of the kind that I keep track of everything. It's all for you guys. Please find out if there is anything.
Okay, Patrick. Okay, so Two questions. One is that with this ND Sengupta transformation that leaves ds square invariant, is there a different group involved? Like Lorentz group comes from the usual.
It is same Lorentz group, because Lorentz group is it's same Lorentz group. It's a different realization, but it's a limit which is not Galilean limit. There's another, which means there's another limit which is non-Galilean, which is the Sengupta limit.
The second point was that you have a torsion in your degenerate theory. Question is whether this torsion is metric compatible, in the sense that is the distance extremization and the parallel trans.
I have not checked it there.
Whether they are.
I have not checked that.
Okay, last
That's a
question.
good question. That's
Last question.
Okay,
Oh, boy.
you.
Okay.
We have to do the next talk also.
Right, so, from what I gather, you didn't mention this much, but just sort of behind the motivation behind this thing could be to have some sort of gravitational incidence, finite action solutions for the Euclidean, right? So the question automatically arises, are there topological quantities which you will associate with this topological invariance? And you try to calculate, I don't know, how would you calculate these things also, it may be difficult. But is that on the agenda?
Yes, there's a systematic way of doing that. And that's what, in fact, I didn't want to get into that, because that's what brought us to this way of thinking. We are essentially trying to explore the question, is there a quantum structure? Is there a structure of quantum? Is there first an understanding of what is quantum vacuum in gravity, and does it have a structure? Like this QCD has a certain vacuum structure. To do that, you need certain finite action Euclidean solutions to it, right? So which would be corresponding instanton types solutions in QCD in gravity. In gravity, there are three types of topological invariants one can construct. One is standard Torsion index, and the other is the Euler. But there's a third one which is less known, and that is neon. Neon has the property that it's completely torsional, which means for configuration torsion, that have torsion 0 is 0. So we were essentially looking for configurations which would carry torsion and therefore would be non-zero when we evaluated their instanton, this neon instanton number. So that is the reason we. So there is a whole set of ideas. That is what is motivating us to doing this.
Okay. Now I'll. Next speaker.